Our last force that we will add, and we're going to talk about it while thinking about it in terms of energy. So I think that is really the easier place to kind of wrap our heads around springs. So this force due to a spring, let's see. If you've ever been to a playground where they have the little teeter-totter toy things that you can sit on top of, and they have these really big Hooke springs underneath them. And so you sit on top of them, or your kid does, because adults shouldn't be entertained by toys on playgrounds, I suppose. But if you sit on top of them, you don't go smushy down all the way. You might compress it a teeny tiny bit, but the spring is Hooke. So compressing it is really difficult because it's a very stiff spring. So Hooke's law just talks about springs in that way. It says that springs become more resistive. This can be a stretch from equilibrium or a compression from equilibrium. So it is going to be equally as hard to stretch a spring out as it is to compress. And the way we define that with Hooke's law is that force equals kx. Now, the one thing I want to look at here as we relate this to energy is because this thing isn't constant. The spring is not a constant. The further out, the harder it is, the more force I have to put into it to get it to stretch that distance. That's where that straight line behavior comes from. So before, when I did the area under the curve, I had this like constant force. And I said, okay, so here's the area under my curve. And we said that this piece here, this force times this displacement, gives me this work. So let's take a look at what that is here. So for a spring then, work for a spring, this is a triangle. So the area of a triangle is, let's see, 1/2 base times height. So 1/2 force times displacement. Well, the force of a spring is kx, so 1/2 kx. Well, displacement is just another x. They're the same. I'm stretching it or compressing it from equilibrium. So these two are the same. So my work from my spring is the area under the curve. It's 1/2 kx squared. The important thing to remember with work from a spring, I realize the one thing I don't have here is this negative sign. There's a reason for that. This negative sign here causes more students headaches in trying to decide if they're adding or subtracting this work done by or on the spring. What you want to ask yourself is just one simple question. Am I compressing the spring? So if I have a spring here and a box moving this way, this box is going to have some amount of initial energy, some amount of oomph behind it, and it's going to hit the spring. The spring, do you think it's slowing it down or speeding it up? It's going to slow it down, right? And eventually it's going to stop unless like this is a really, really heavy box and it's going to break through the wall. So that spring is taking energy out. If I have something in terms of energy, which is our very next topic, then this component here, like friction, would be negative. If I have the reverse, where my box is, here we go, let's shade it in. My box is now compressed the spring. So there's springiness in here, and the spring is going to push it out. Here, the spring is going to do work on the box. It's going to add energy to it. So then I would make the sign, or however, we'll talk about conservation in the next video, appropriate to having energy added in. So then this one would be like going out of that away. So the spring is doing work on it. Here, I'm doing work on the spring. Let that guide you as far as what sign you're going to have, and don't worry about that for now. Actually, I suggest don't. It's going to mess you up in all sorts of ways.